Hello everyone. In this video, I'm going to demonstrate how we can experimentally determine the moment of inertia for a solid ball by analyzing its motion down an inclined plane. The moment of inertia, I, represents object resistance to rotational motion for most symmetric bodies. It follows the formula I is equal to c mr square, where capital M represents mass, capital R is radius, and small c is shape dependent coefficient. Our goal today is to find this value c for this ball. By applying Newton's second law for both translation and rotation, we can derive a linear relationship between the ball's acceleration a and the sine of inclined angle sine beta. The slope of this relationship, which we call k, allows us to solve for c by using the formula c is equal to g by k minus 1. So to conduct this experiment, I used a solid ball, a stable rack. In my case, I used a thick cardboard, at least 1 meter long, a tape measure, and a stopwatch. Maybe if you want to use, you can use a mobile phone or anything. It is vital that the track doesn't bend during the runs. And the procedure is simple, but requires precision. So I measure the time it took for a ball to roll down the length for 5 different heights for each angle. I perform the 10 trials to get a reliable average. I then calculated the acceleration using a is equal to 2L by t square. After calculation, looking at my data table, you can see the acceleration increases as the sine of the angle increases. I plotted this points and performed a linear regression. The slope of my best fit line was approximately 7.33, which a very strong correlation coefficient of 0.984. Using our slope k, I calculated the experimental value of c to be approximately 0.34. Theoretically, a solid sphere should have a c value of 0.4 or 2 by 5. Then when we calculate absolute and relative error calculation, the result gives us an absolute error of 0.06, while in my report mentions relative error calculation of 0.15. A standard calculation actually places this at above 15%. This is a reasonable margin for a home conducted experiment. And that's it for this video. Thank you very much.